progress.
Okay. Welcome to this afternoon session. So our first speaker is Dr. Chiheb Ben Hammouda. Chiheb is a postdoc at the chair of mathematics for uncertain quantification at RWTH Aachen, and he will soon move to a new position as an assistant professor at Utrecht University. So Chiheb will talk about importance sampling for the estimation of rare events within the framework of pure jump processes.
Thank you, Nadir, for the kind introduction. First, I want to thank Raul and AJ for organizing this nice workshop where we enjoyed the mini course offered by Christian and Eduardo, and also a nice variety of talks. Today, my talk will be about automated importance sampling via optimal control for stochastic reaction networks, and we will propose two approaches. This is joint work with Nadir Berrached, Raul Tamponi, and also Sophia Wichat, who is doing currently her PhD at RWTH Aachen. Okay, so let me give you a snapshot of the ideas that I want to convey during the talk. So basically, the talk will be about designing efficient Monte Carlo estimators for relevant probabilities for a particular class of continuous time Markov chains that are called stochastic reaction networks. And this is based on derivation of automated path-dependent measure change based on connection between optimal importance sampling and stochastic optimal control formulation. And when we will go to solving the resulting optimal control problem, we will address the cursive dimensionality through two ways. The first approach, we follow learning-based kind of approach where we learn the value function and the controls based on an approximate dynamic programming problem and stochastic optimization. This was the topic of recently appearing paper in statistical computing. And for the second approach, we will follow Markovian projection-based approach, where instead we will solve significantly reduced dimensional HJB equations compared to the original problem. This will appear in a couple of days, hopefully, and you'll find more details. Okay. You hear my voice well, right? Okay, very good. So in this talk, I will follow the following outline. So first, I will start with certain motivation and explaining the framework we consider. Then I will explain the formulation of how to derive optimal path-dependent importance sampling via stochastic optimal control. Then I will show the two approaches that we follow, the learning-based and the Markovian projection-based approach. And before concluding, I will show you numerical results highlighting the advantages of the approach that we use. All right, so let's start with a certain, so let me also tell you that, so this talk will be relevant for people that work with stochastic reaction networks, but also there are a lot of ideas that you can adapt to your problems in case you have a different stochastic process also. All right, so stochastic reaction networks, what is the motivation? So as some of you may know, deterministic models describe an average behavior or macroscopic behavior and are valid only when you have a large population or the mean field kind of limit in your problem. And whenever you have in your system species or agents with small populations, then the dynamics will be dominated by stochastic effects. So stochastic reaction networks are a way to model these stochastic effects using Poisson processes. And there are a bunch of applications that can be very relevant to model with stochastic reaction networks, like biochemical reaction and biological models, modeling the epidemic, the spread of epidemics in time and space. Also, they were used to model manufacturing supply chains and logistic networks, modeling also interaction in social networks, multi-agent networks like autonomous vehicles, and also distributed systems through Petri nets. And also they were used in transcription and translation in genomics and virus kinetics. So there is a wide applications, I mean, that can be modeled by stochastic reaction networks. Now, formally, what is stochastic reaction network? Basically, it's a continuous time Markov chain that is defined through the state vector X here, where the component of the state vector basically refers to the counting number of the abundance of the E species or agent in your system at time t. And the interaction between these agents is described through G reaction channels that are characterized by the pairs nu J and AJ, where nu j basically are called stoichiometric vector, or you can see them as a state change vector, and aj are propensity functions or jump intensity functions. Usually aj has a polynomial structure, and this is due to the mass kinetics principle. So in this setting, the propensity satisfies the following relation, which says basically that the conditional probability, a condition on the state at time t to be at position x, to observe a jump due to the firing of the dish reaction is proportional to the length of the time interval, and the constant of proportionality is equal to the propensity evaluated at the current state. So this is an important relation because it's used to derive the chemical master equations, but also to derive an important representation for these systems, which is the Kurtz random time change representation, which is used to design the different simulation schemes of such processes. So, so in this representation, basically you model the evolution of the state process using here summation over, so this is unit random variables that has a rate that is equal to the integration of the propensity that depends on the state. So this term will model the occurrences of the number of reaction j, and here you multiply it by the state change vector nu j to get your state vector at time t. And here you see some illustration of when simulating exact path using this representation, and you see that you can have reactions with slow rates, where here the associated propensity basically will be small, or you can have also fast reactions when the propensity is large. Okay, so based on this representation, one can use pathwise exact simulation schemes, basically by modeling the exact distribution of the process. Such examples include a stochastic simulation algorithm and modified next reaction method. So, for instance, the stochastic simulation algorithm tries to sample at each time two random variables, one that gives you the first time to have a reaction, and the second one will give you which reaction that will be fired. And you can imagine that if you have reactions that fire with high rates or higher propensities, then you need to sample a lot of random variables, and this makes somehow the simulation very expensive. That's why we can sacrifice with a certain bias and then introduce a faster pathwise approximation. And the most popular scheme in this setting is the Explicit scheme, which was introduced by Gillespie in 2001. But also there are other schemes. For instance, last year with Alvaro and Raul, we introduced the split-step implicit loop, which is relevant for stiff systems when you have different multi-scales in your system, like fast and slow reactions. And also this scheme was compatible with multi-level Monte Carlo that we used in that work. Okay, so we will focus in this work, in this talk, sorry, we will focus on the explicit Taulib scheme. So let me briefly explain what is it. So it's based on the course time change representation, and it's kind of forward Euler in this setting. So what you do, you freeze the propensity basically at each time interval tn plus 1 at the left part, and then what you get basically, you get this sum of Poisson random variables that has rates that is equal to the propensity evaluated at the current state times delta t. Okay, here we use the maximum because usually we deal with counting number of species of agents, so it should be positive. One way to ensure that is to project to 0. So there are other ways, but this is one way. And again, here the Poisson random variables are conditionally independent. So this is to keep in mind. All right. Okay. So this talk will be mainly about importance sampling. So I think most of you know what is Monte Carlo. Let's motivate briefly why we need importance sampling and why it works. So for illustration, let's consider random variable y. So importance sampling basically tries to sample on the regions where you have most effect on the quantity of interest, where you match the function that you want, I mean, to compute its expectation. And okay, instead of approximating your quantity of interest using Monte Carlo, but with respect to the expectation with respect to the original measure that I denoted here by P, what you can do is that you write a slightly different expectation with respect to a new measure Q, and then you compensate the term here by introducing a likelihood factor or Radon-Nikodym derivative. and then you use Monte Carlo on top of that, okay? Now, why this is paying off, right? And this can be seen through the minimum variance that we can achieve. So if we consider Q star as the measure that gives you the minimum variance after doing this change of measure, then you can show that the variance of this term basically will be equal to the product of this term and this term. So you can get a zero variance if your random variable y has a near constant sign under the new measure, or you can also get advantage if you have the variance of y over the square of the expectation of the modulus of y is much greater than 1. And then you get a variance reduction compared to computing your Monte Carlo with the original, with the expectation with respect to the original measure. And of course, you introduce this factor to take into account that you will sample with a relative cost additional to when you use the change of measure compared to the original measure. Okay? Please interrupt me at any point if you have any questions. Okay, so let's now motivate what we will do. So the aim and the setting of this talk is the following. So we want to design a computational efficient Monte Carlo for approximating the expectation of a certain observable of the process at terminal time t. And we want to use importance sampling. So we are interested in relevant probabilities, which means that the G or the observable here will be an indicator function, and the probability that the process at terminal value to B and the subset B basically will be very small. And the process here will be a stochastic reaction network. So the challenge, I mean, as I explained maybe earlier, is that, So to get this Q star is not something easy. I mean, this is kind of, it gives you some insights that you can shoot for it and get a good measure, but usually it's not very easy to get a good importance sampling. So it requires some insights into the given problem. So our solution basically is to suggest an automated path-dependent change of measure that is based on the connection between finding the optimal ES parameters and the stochastic optimal control formulation, which corresponds basically at solving to solving a variance minimization problem. So this will be what we were showing later. Okay. So let's start with the formulation of this connection. So the first thing is the class of probability measure that we will concentrate on. So for that, I will first recall the Taulip approximation. This is something that I explained earlier. And what we will do basically is that we will consider the change of measure in somehow the same class of measure, which is driven by the Poisson and the variables. And what we will only do is to change somehow the rates through the propensity. So instead of using the original propensities, we will use these control parameters, and this will be optimized to get the optimal or the minimum variance. I should note that a similar class of measures, we have used it in another work with Raoul and Nadir, and it was for the purpose of improving the multi-level estimator in terms of coupling. So here, as you see, the control parameter will be dependent on the time step, the reaction G, and also the current state vector. So this will be somehow a tensor of parameters that you need to solve. And the admissibility set is given by the following. So basically, these controls will be 0 whenever you have the original propensity is equal to 0. Otherwise, they will be strictly positive. So this is the admissible set of this problem. Okay, so as I said, we want to find the optimal importance sampling parameters that will result on the lowest possible variance. And for that, we first need to introduce the value function that we will consider for stochastic optimal control formulation, which is basically given by this infinimum so the second moment of the quantity of interest, because basically the importance sampling will not change the expectation. So basically, we just need to minimize the second moment. And you see here that the second moment will involve the square of the observable at terminal time times this likelihood factor. And by using the conditional independence, you can write this likelihood factor as a product these terms. And here also we use the advantage of our class of measures, because once we use a Poisson measure, we are able to get a nice expression of the likelihood factor, which will be important later on to make the formulation more straightforward. Another note here is that compared to, maybe you see it from the value function, is that compared to the classical stochastic optimal control formulation, here we consider the expected total cost to be in a multiplicative cost structure rather than additive one. Okay, and so once we introduce the value function, we know that we can have a set of backward equations or dynamic programming relations that will give us a recursive way to compute the value function. And this is somehow what we derived for the following context. So here you see the dynamic programming relation that relates somehow the value function at time n and position x to the value function at a later time n+1. Okay, and these terms basically will come from the likelihood ratio that I explained earlier. And you see here that this term would be including an infinite sum over all possible the Poisson increments that you will have. And of course, the final condition will be the square of the observable at the location x. Okay, so this is nice. We derived the dynamic programming, but the problem is that it's difficult to solve this analytically. Why? Because of this infinite sum. So we need to do some approximation and get an approximate dynamic programming relation, so we'll be able to solve it numerically. Okay, and this is somehow what we do. So what we do, I mean, if I go back one slide, so what we do a Taylor expansion of this exponential, and what we do then is to do an approximation up to leading term that is O of delta t squared. And this is now leads to much nicer problem. So here, this is the approximated value function with this is the terminal value cost, and this is the dynamic programming relation, where here you see that this term basically looks much better because it decouples the control parameter from each other. So instead of having this optimization that includes non-coupled control parameters, so it's hard to solve it. So you solve it in simultaneously over the G reaction. But here, thanks to this approximation, now you can have G optimization problems that you can solve them in parallel. A nice thing also here is that we could derive explicit solutions of the controls that will depend, that are related somehow through the value function. And this is given by what we called here delta bar. Again, this is for each time step, for each reaction, and for each position or location of the state vector. So, okay, I note here that to get this explicit solution, we require basically some condition on the value function. And we can ensure these conditions either by doing some regularization or by modeling the value function through a strictly positive ansatz, as I will show later for the learning-based approach. So this is not a big problem, but still we can exploit the structure that we get from the approximate dynamic programming problem. Okay, so one can say that, okay, I will solve this optimization problem, but the problem then you need to solve it for d-dimensional state vector. So you need to sample over the state space, and this will, let's say, imply what is called the cursive dimensionality, because the cost will be scaling with respect to the dimension. So here S bar is somehow the upper bound, the maximum upper bound over the different dimensions. So then we need to have some tricks somehow to avoid this cursive dimensionality. Again, here what we will do, we will still exploit this structure that we derived in the approximate dynamic programming that relates the controls to the value function. And the main thing is how we can get this value function in a much efficient way than solving the full dimensional approximate dynamic programming problem. So the first way basically that I will explain later is to model the value function through a parameterized ansatz function. And then you learn somehow the parameters, the vector parameters beta that you include through stochastic optimization. This approach is attractive whenever you can introduce a relevant ansatz to your problem. And as an alternative approach, we propose also an approach that is based on the Markovian projection. And in that case, what we will do is that instead of solving the approximate dynamic programming, as I showed you in dimension D, we will solve it in a significantly, we will solve actually the related HJB in significantly lower dimensions. So we try to reduce the effect of the cursive dimensionality. And again, this is somehow suitable when the projection dimension is very low. So you may consider this approach as complementary, or they can be attractive for some cases and the others for other cases. So this is what will be the topic of the next parts. Any question? Okay, good. Okay, let's start with the learning-based approach. So this is the illustration how we work with the learning-based approach. So we start with the full dimensional stochastic reaction networks. And then the idea is that we will model the value function through a parameterized ansatz. You can think, in general, as a neural network or some ansatz that depend on the structure of your problem. Then what we do is that at each iteration, we need to sample important sampling paths that are parameterized also. We will show that we can get explicit derivation of the gradients that will help us to update these parameters through the stochastic optimization. And then once you recover a good, let's say, convergent value of your parameters, so a good ansatz value function, a good, let's say, terminal value of your value function, then you plug them through, let's say, this relation that you saw here. So we just plug now the value function that we end up with, and then we get the optimal importance sampling parameter. So then we are able to derive an efficient Monte Carlo estimator. So this is somehow the illustration of the approach. Now, in more details, how we do that, I remind you that, okay, we have the value function coming from the approximate, this is our value function that we have in our case, right? So the idea is that we will introduce now an ansatz function that is parameterized through the parameter beta. So as illustration, you can, if we have an indicator function for the terminal value, so when we compute probabilities, then we propose such an ansatz, which seems to be very, very good in this context. And you can see basically that such kind of sigmoids are very suited, to this kind of problem. So here in this ansatz, we will have two classes of parameters, which are in blue and red. So the blue parameter, which we call here beta space, which will be somehow modeling the effect in the state space, and beta time, which will model the effect in time, will be learned through stochastic optimization. So these are D+1 parameters. And beta 0 and B0 will be parameters that are fitted to the final condition, okay? So you see here that if you take T, so here we work with scaled time. So if you take the final time, basically, you see that the beta B0 and beta 0 will give you somehow the good fit for the slope and the steepness of the ansatz function. Okay, so once we introduce the ansatz function, I should say that, in general cases, you can have other ansatz if you have insights on the problem. Otherwise, you can use a neural network and you try to learn, with more than one neuron. So once we introduce the ansatz function, now we reformulate the problem with respect to the parameters. So now we want to learn these parameters beta. So the problem now becomes to compute, to minimize this second moment, but the paths now are generated using these parameterized controls. So as you see, they will depend on beta through the value function, because the ansatz is through the value function. And then at each somehow iteration, you get some controls. With them, you can simulate this kind of changed measure paths that here we parameterize by x bar delta t beta. And then also you obtain the corresponding likelihood factors. The good thing why, I mean, we can use efficiently the stochastic optimization also because we could derive explicit pathwise derivatives, so they are unbiased, so we don't have to use final difference, but we just have to estimate them through the Monte Carlo method. And basically, this is given by the following lemma. So basically here we show that the partial derivative that will constitute the gradient with respect to each parameter of the cost function will be having this nice expression. So you have the expectation of the following term. So this term basically is the same as the cost function that you start with. This is somehow sum over time and the number of reaction of terms that depends on the new controls. And you have a derivative of the controls with respect to the parameters. The nice thing also here is that it's we can find in a closed form this derivative. Why? Basically, because these controls are again expressed to the ansatz or for the value function. So we can have access to those derivatives as well. Okay, so once we get, I mean, this optimal beta that minimizes, I mean, the second moment, now we can plug them on the Monte Carlo estimator. So we simulate the paths now using the beta star that we converge with, and with the controls basically that corresponds to the following structure. And then we obtain an efficient Monte Carlo estimator, as I will show you later. Okay, so now let's, yes, Andre. Yes, here? Yeah, I mean, yes. I mean, yeah, the thing here is that, I mean, we still are able to get, I mean, the explicit way of the, but I mean, you can also use the transformation, I mean, the logarithm transformation, so.
Yes, because it's bounded. I mean, you're a meeting point.
No, because sometimes you can get
better properties, you can get maybe convexity. Very often it's log complex.
Yeah, but in our case, I mean, you don't have, I mean, guarantees that you end up with a convex problem with respect to the parameters, because, I mean, you see, so the parameters are related to the controls to this value, ansatz value function. So it will depend maybe on the ansatz function, but still, I mean, you cannot say something about the convexity of your problem.
Okay, thank you.
Yes, Fabio. Sorry? Yes. I mean, okay. It does not depend. Okay, it should. I mean, maybe I'm using sloppy notation, but it will depend somehow through the value function, because what you care about. Okay. Let me. Yeah. Okay. No, it's not, because, okay, this is the beta, right? So this is, it has component in space and in time. And you see that this is kind of constant, does not depend on t. Yeah, I need to solve the optimization problem. You get, after one iteration, a new beta. This will give you the new No, we don't solve any HJB here. So, okay. But I mean, okay. So what we do, okay, that's a good question, maybe to. So what we do, we will exploit the structure. So this is use the dynamic programming. We will not solve the dynamic programming. The idea is that, okay, you can get now an approximation somehow of your value function through the learning-based approach, through the ansatz. And what you do when you parameterize your parameters, so you end up with this U hat, and then you have an optimization problem over your parameters. You get your parameters, you construct your controls, then you can simulate your paths. And so, I mean, this is also corresponds to this illustration, maybe that. So here we learn, we don't solve any HJB or dynamic programming. We learn until convergence somehow the parameters, we get the final controls, and then use them in the forward run for the Monte Carlo. So up to here, for first approach at least, we don't solve any HJB or dynamic programming. Answer the question? Okay, thank you. Yes, Christian.
Back to the same question.
Yes, sure.
So just
Just so that I understand, instead of solving a dynamic programming equation, which means you solve like, let's say many small optimization problems, you solve it global.
Yeah, but then you don't have the cursive dimensionality that appear if you want to solve it. I mean, because anyway, if you want to solve this, you will be kind of killed by the state space that you have. So if you okay, this is discrete, so you don't have this guy. But if you want to have a certain support of your state vector, then the cost will scale like still exponentially with respect to dimension. Of course, okay, we move this to an optimization, but usually it's much better. We show this that it's much better behaving than solving the full dimensional thing. Yes.
Okay. There are two value functions here, right? One that is actually the one that includes us and answers, and then basically the parameters, which is used for the sole purpose of creating the important sample scheme. But the actual value is going to be computed much more accurately via the Monte Carlo using this important sample scheme. So it can be rougher when you created the important sample scheme, which is we have to be accurate enough when you apply, and therefore that answer is on things for the computation of the expected value.
Yes, Fabio.
Given this optimization on beta, so you solve the path that you start from what point?
Okay. Yeah. So first you have this fitting parameter, right? So at the final time, which is 1 here, you don't have this parameter. So you can start with initial guess, but this will determine somehow your initial ansatz that matches the final condition. So if you have an indicator function, so the beta 0 and b0 will give you, this depends with respect to the state space, right? And then, so once you start with that initial value, then you learn, the blue controls, that will model the dynamics of your value function through time now and space. Okay, very good. All right. Okay, so then now we can go to the second approach, which is on how to use Markovian projection as a complementary approach to the learning-based approach, because sometimes, you may not have a good ansatz, and also you can have like a big optimization problem that can be also problematic. So, okay, what we do here, first I show you the corresponding Hamilton-Jacobi-Bellman equation to the approximate dynamic programming that I showed earlier. So here we will have actually a system of ODEs, in this setting. So you only have the derivative with respect to time of what I call here U tilde, which will be the solution of these HJBs. And again, if you have the condition that your value function is strictly positive, you can enjoy having this closed solution of the controls that are linked to the value function by this formula, and then you need to solve this system of ODEs for the value function. The same problem here will happen as I explained earlier. So if you want to solve it in D dimension and for your full dimensional process, then you will have the cursive dimensionality. So we don't want to do that. And that's why we want to do the Markovian projection. So basically, we start with this full dimensional stochastic reaction network, right? And instead of doing the HJB that I showed you and then have the controls and then have the Monte Carlo estimator, what we do Markovian projection. So the Markovian projection will be dependent on the quantity of interest, but then you will end up with a projected process that is still a stochastic reaction network, as I will show you later, and it will lie in a lower dimensional space, which I denoted here by d bar, which we can even have it once, so it will be much less than the dimension d. And once we have this projection, then we can now solve the similar HJB here, but in a lower dimensional space. So it will be in d bar dimension. Then you can get your projected importance sampling control, and then there is a way to map it back to the original system, and then you get an efficient Monte Carlo estimator. Okay. Okay, what is a Markovian projection basically? So first I recall you about the Kurtz random time change representation. So the evolution of the state vector here is given by the following representation. So if you take any projection to the D bar dimensional space, you can see that if even, X here, the stochastic expressions are Markovian, sorry, the projection is not, okay? So this is problematic. And basically in this setting, we want to adapt the idea that originally was introduced by Gronji for the setting of diffusion type SDEs to the stochastic reaction network and using importance sampling. I should note that Christian and Raul and you, I think, they used a similar kind of projection, but for solving the problem of American option pricing, right? So this also we used for that purpose. In here, we want to adapt it to the stochastic reaction network framework and derive an optimal importance sampling through it. And as I said earlier, the projection usually will depend on the quantity of interest. So if, for instance, you are interested in these probabilities, then a very relevant projection will be to just project to the ETH component, and then you can work with it in 1D. I mean, if it's good a projection. Okay. Now, the problem, basically, as I said here, is that this is a non-Markovian. So the idea is that we want to construct a low-dimensional Markovian process that will mimic the evolution of S. So because S is not Markovian, so the main idea we want to construct this low-dimensional Markovian process that will mimic the evolution of the projected process. And this is given by the theorem that we showed here. So again, we consider this projected process S, as I defined earlier. X will follow the Kurtz representation that I showed also earlier. And if we denote now S bar to be the D-dimensional stochastic process that has this dynamics, so if you remember, well, it has similar representation as Kurtz. What changes is that for the initial condition, you have this projected initial condition. Now you have different propensities. So the propensity we denoted here by I bar, which are the projected propensities. And for the state change vectors, there will be also the projection of the original stoichiometric vectors. Now, what we can show basically is that this D-dimensional, D-bar dimensional stochastic process will have the same conditional distribution for any time as the projected process. This can be if we choose the propensity to be equal to the conditional expectation of the original propensities with conditional on the projection at time t to be S and the initial condition of the state vector X. Now, I'm not showing maybe the proof, but the elements of proof somehow are not so complicated. So first, you want to show that they have same conditional distribution. So you look at the weak approximation error, and you want to show that for any bounded function, you end up with a zero value. And this can be ensured if you choose the structure of the projected propensity. So you try to express the things as difference between the generators, that one that will be related to the original process and one to the projected process. Use the Kolmogorov backward equation, and then you can get such equation that characterize the projected propensities. Okay. Okay. So one interesting thing that you can see here is that compared to the original propensity, you see that the original propensity does not depend on time. So they are homogeneous with respect to time. An interesting fact here is that the new propensities will be dependent on time, okay? So this is something that is different compared to the original propensities. Another thing is that we do not have to project all the propensity for all reactions. Why? Because, for instance, for reactions where you have the projected state change is zero, you don't have to compute any project propensity, or if your original propensity is only a function of the projection, then, you get the exact, expression. So you don't have to do any computation of the projected propensity. Otherwise, so if we consider the set that excludes these two conditions, then we just, formulate this condition expectation as a minimization problem, and then you can use a discrete L2 regression to derive an approximation of your projected propensities. So here you just introduce a certain class of functions. You do your minimization of the integration in time of the second moment of the expectation, sorry, the second moment, yes, of the difference between the original expectation times over all functions h that are in the space V. All right, so what, yes, Fabio. Sorry? Yeah, but the full process is given, right? I mean, this is the original process, right? So if you, this is, yeah, I mean, that's okay. That's a good question to solve. I mean, when you solve the, yes, of course, you need to simulate it, and then you create. I mean, you do kind of you create orthonormal based function, and then you try to because this. I mean, the basis will be based on empirical distribution. So you need to simulate them and then solve your normal equations, and then get, I mean, your A bar expressed on the basis function that you introduce. But yes, you're right. Okay. So now we have all steps to perform the Markovian projection. Sorry, to have the importance sampling through the Markovian projection. So as I explained earlier, we do the Markovian projection as I explained in the previous slides. Then the nice thing, we will end up now with a lower dimensional HJB that will lie on a D bar dimensional space. So we have more or less the same structure of the HJB that we had before, but it will lie in a lower dimension space. And here you will have, instead of the original propensity, you have the projected propensities. And we will exploit the nice structure that we had derived for the controls. So once we got the good approximations via solving a lower dimensional HJB, we plug them in this relation, and then we get our new controls based on the Markovian projection. And you see here that the mapping back, basically, you see that we map back through the projection. So you can express your project propensity in the full dimensional, but still using the projected value function somehow. Okay. Okay, so now let me show some results, I mean, that highlights the advantages of the different approach. So I will show some results corresponding to these examples. Maybe you don't have to care a lot about the examples. What I want to show basically is that this problem will have a dimension 4 and 3 reactions, and we will have a probability that is of order 10⁻⁵. This enzymatic futile cycle model will have a 6-dimensional species problem and will have 6 reactions. And the Gutias model basically will consist of 6 species or agents and 10 reactions. So, and the probabilities here for the first problem will be around 10⁻⁵. This is 10⁻⁶, and here 10⁻�3. Okay, so they are relevant kind of probabilities. Okay, so the first plot here, it shows the results for the learning-based approach for the first example. So first here, this is the mean. Okay, so you compare the standard Monte Carlo, plain Monte Carlo without doing anything with respect to approach. Okay, nothing very interesting here maybe. But then here by looking, okay, we look at the square coefficient of variation because we deal with the low probabilities, so it's more relevant than tracking the variance. And you see that you have order of 10 to the, 1,000, 4,000 of gain, and this is achieved through the initial iteration. So somehow the good fitting that we did initially somehow helped us to not have a lot of iteration, because again, iteration stochastic measure will be costly because you need to sample the important sample path. But here the nice thing is that we get very good variance reduction through the initial iterations. Okay, so here also we show how the different parameters in space and time looks like somehow with respect to the iterations. And also the nice thing, also we have controlled kurtosis compared to the tau leap. Kurtosis are important to make sure that your estimates of the variance or square coefficient of variation are robust. The same thing happens for the larger dimensional problem here and a lower probability. Again, this is the mean here. Here you observe that we have around, after kind of 43 iteration, we have a 50 ratio of reduction with respect to the tau leap, the standard Monte Carlo. And again, we have a controlled kurtosis compared to the original estimate, the plain Monte Carlo estimator. There is another interesting thing. if you remember well, you have two kinds of delta t's, right, for the learning-based approach. There is the delta t with which you learn your parameters, because you need to sample the ES paths until convergence. And also there is the delta t of what you care about in the Monte Carlo. So at each delta t, you want to have forward run of the Monte Carlo. And you see here, by using a coarse delta t to learn the parameters, we basically achieve a similar variance reduction. I mean, so what it tells you basically is that you don't have to spend a very large number of time steps to learn your parameters. So you can do it in a coarse level. You get nice controls, and then you get somehow similar effect for later delta t. When you do the forward run, you can use the controls that you learned in the coarse levels, and then use them later on for your final delta t. So this will reduce somehow the cost of the learning, right? Because you don't have to spend too much in discretization. All right, so let's show some results related to the Markovian projection. So if you remember, where the first important thing is to ensure that you have the same conditional distribution of the projected process with respect to the S bar somehow with respect to the projected process. And here we show somehow these histograms that shows somehow that you have a good approximation of in terms of distribution with respect to the original the projection, which is equal to P times the original process X. I should also make a important note here is that since we care about importance sampling and a decrease in the variance, we don't have to solve this discrete L2 regression very accurately, because you can be kind of loose in solving it, but still obtain a very good reduction. And basically, when we use, I think the order of base function was quadratic with respect to time and space, and we still observed this kind of gain. So you don't have to do very expensive regression as well. And here, for the first example, we show similar things. So here, this is the mean, and here you get again like 1 million of factor. I mean, if you go maybe to the fine time step 2 to the power minus 10 with respect to the Monte Carlo, which is a big thing. I mean, in terms of how many samples you will use in the forward run. And the same thing, okay, maybe also I should make this note, is that in this case, the projected dimension is equal to 1. So this is somehow makes also solving the HJB still affordable, right? I mean, otherwise, maybe we need to do other tricks. And the same thing here for the second example. So we get a factor of 500 at the deepest level here, somehow 2 to the power minus 10 compared to the plain Monte Carlo estimator. So these things shows the advantage of both approach. So as I noted earlier, in those examples, the projected dimension equal to 1 was sufficient, but of course you could have problems that you need to maybe higher projection dimension. But the idea there is that you can use this adaptively, right? So you start with 1 projected dimension. If you are not happy with the variance reduction, then you can increment, I mean, your space, projection space, and then until you are happy somehow. So you can do this adaptively, okay? However, of course, this comes with an increased cost in the when solving the projected HJB. But still, you can do also other tricks on top of that. But so this opens, I mean, interesting things to do for variance reduction. All right, so then let me conclude. So basically, I showed you how we design efficient Monte Carlo for the class of stochastic reaction networks when computing relevant probabilities. We did this through this novel kind of connection between automated path-dependent measure, between optimal quantity sampling and stochastic optimal control formulation. And we addressed the cursive dimensionality through different ways. The first one was based on learning the value function and stochastic optimization. The second one was based on the Markovian projection. And as I showed you, the analysis and numerical experiments show that we get a very good variance reduction ratios compared to using the plain the standard Monte Carlo estimator. So these are related references to this talk. So this one is related to the Markovian projection. Hopefully it will appear in a couple of days. This one is related to the learning approach if you want more details. This one, what I can say also for the future work, somehow one can try to combine what we did for the multi-level, for the coupling levels, and because this one was kind of the single level, so you can think about it as the coarse level variance reduction. So then you can combine both, or also you can try to do similar tricks, but for the coupling levels. And also we can extend this to implicit schemes. So we can also use the ideas that are here, but using implicit schemes instead of using the explicit scheme that I showed you earlier. And then thank you for your attention.
Thank you, Chiheb, for the nice talk. So do you have questions? Fabio? Yeah, thank you. I will ask many more questions later.
No, you're welcome.
No, two questions. One, in this Markovian projection, how much do you lose if you don't do this linear regression and you just take the rate evaluated in the projected state?
Can you please repeat the question?
Instead of matching this conditional expectation, you just evaluate the rate in the projected state in the dynamics. Instead of correcting the A bar, you just take the original A.
So
how much do you
let
lose?
me understand. So we will have to compute these conditional expectations, right?
Yeah, these if you want to match, but if you just in the evolution of S bar, you just use A instead of A bar, how much do you lose in terms of accuracy?
Okay. So to see how this compares, yeah, but I mean, you see, right? I mean, because, I mean, okay, let me understand your question again. So,
If you take A,
yes.
you fix the variable that you're not going to take into account.
Mm-hmm.
It's good as a way to create a.
So far, no. I mean, I think we tried this and it was not giving good results. So using the regression gives you much better results. And as I said, we did not have to, I mean, the regression was not in very fine basis function. I mean, quadratic in time and space was sufficient. Is this answer your question?
Yeah.
Okay, that's.
The second one is how do you choose these directions? I missed at this point.
Which one?
The projected directions.
Okay, yeah. So, oh. I mean, this somehow will depend on your quantity of interest. So, I mean, if you have an indicator function
in
of
this example is clear. I was asking in general, how would you?
I mean, it's kind of cooked. I mean, you cooked it depending on your example. I mean, you can still start with something, as I said, you can start with something that gives this. I mean, first you need to see your quantity of interest, how it depends on all the state space, right? If let's say it depends on two from the D dimensions. So one thing is that you can take, I mean, you project to that thing, maybe the sum or something like that, and then start with it. Maybe it gives good results. Otherwise, you need to adaptively maybe add other components. But once you look at your quantity of interest, you can get a feeling that maybe your quantity of interest does not depend, maybe it depends only on the sum. So then you project to the sum of all the D dimensions, and then you concentrate on the first dimension, but you don't care about the transformed vector, you don't care about the other components. So this basically depends on the quantity of interest that you are trying to approximate.
Thanks.
Thank you.
Well, do we have more questions? Okay, if not, let's thank Chiheb again.
Thank you.
Our next speaker is Sebastian, so we have 3 minutes, so we can take 3 minutes break, 2 minutes break, while Sebastian